So now let's move on to IBM Model 2. IBM Model 2 is, as we'll see, a fairly straightforward extension of Model 1. So the only difference is going to come in the alignment model. So IBM Model 2 introduces what are called alignment, or sometimes called distortion parameters. Okay, so I'm going to use Q for these parameters, and it's going to have a few different indices here. So M, as before, is the length of the French sentence, and L is the length of the English sentence, and J is the index of the French word, and I is the index of the English word. So let me give you an example. So again, come back to this example. The dog barks. And say we have M is equal to 3. We have 3 French words. And let's say, so let's number these 1, 2, and 3. So the second French word, say we align this to the third English word. The probability of this happening is Q of, so this 1, 2, 3, the English position 3, conditioned on the French position 2, and the length of the two sentences, so L and M are both equal to 3 in this case. Okay, so conditioned on the length of the English and the length of the French sentence, and conditioned on the position of the French word we're considering, position 2 in this particular example, we have a distribution over all possible alignments. Again, 0 is taken to be the null word, and that is one possibility. We'll come to a concrete example in a moment of this, but here, abstractly, is how we write this out. So an alignment is again going to be a sequence of variables A1 through AM, specifying for each of the French words what it's aligned to. And to calculate the probability of an alignment, we just multiply together the Q variables. So I have the product from J equals 1 to M, and I have Q. A sub J is going to be the position in the alignment for the jth word. I condition on the position J, the length L, and the length M of the English and French sentences. The final form of the model is then going to be the joint probability of F and A conditioned on E, and this length M is a product from J equals 1 to M of Q times T, and these T terms are exactly the same as we saw before. So this is T of Fj given E of A sub J. Sorry, this is a J down here. So let's work through an example. So again, consider this example where I have this English sentence and this French sentence, and the lengths of the English and French are 6 and 7 respectively. And let's consider this particular alignment I showed you before. I'll just draw it here. It's this particular alignment. So what's the probability of this alignment conditioned on the English word and the length of the French sentence being 7? It's going to be a product of Q terms. So the first term is the probability of position 1 in the French being aligned to position 2 in the English, conditioned on these two sentence lengths. And you'll see that I have a similar term for each position in the French, 1, 2, 3, 4, 5, 6, 7. Each of these positions is aligned 3, 4, 5, 6, 6, 6, respectively. And so this product of Q terms gives us the probability of this alignment conditioned on the English sentence and on the length of the French sentence. So this model is incredibly naive. It misses all kinds of important linguistic properties. From a linguistic point of view, it's really not a realistic model of translation. But the important point is that in spite of this, it gets us off the ground, and it will actually be quite successful in recovering good alignments between different sentences in our training samples. And those alignments will form a critical component of the phrase-based translation systems we'll see a little later in this class. So, a naive model, but in practice it does quite a good job. Here's the second part of this model. Remember, the second part is to define the conditional probability of the French sentence given that we condition on the English, the alignment, and the two lengths. And in this case, it's exactly the same as Model 1. So again, remember this alignment is the following. And so we have one term for each French word, and at each point we condition on the English word which is being aligned to. And we have these t parameters reflecting the conditional probability, for example, of le being translated from there, and so on and so on. So this is the second part of the model. It's the same as IBM Model 1. So finally, to get some intuition, let's consider the generative process underlying the model I've just shown you. It's basically assuming that a French string f is generated from an English string e using the following process. So again, we're conditioning on e being some sentence, for example, the dog barks, and we're going to condition on the length of the French sentence m, for example, m equals 3. So in the first step, we choose an alignment from the set of possible alignments with this probability. So for each word in the French sentence, we choose an alignment to some English word. Okay, and this is dictated by these alignment parameters, these Q parameters. In the second step, we fill in the French words one by one, conditioned on the English word we're aligned to. So something like this. And so that's the second step of the process. The final result of all this is that the joint probability of f and a conditioned on the English sentence e and the length of the sentence m is the product of these two model terms, and so I end up with this model form. I have a product from j equals 1 to m, and for each j I have both a distortion parameter and also a translation parameter. So I have q of a sub j conditioned on the position and the two lengths, and then secondly I have the translation parameter, the probability of fj being omitted from e sub aj. This is the probability of omitting a French word from the English word that is actually aligned to. And that is it. That is the final model form for IBM Model 2. So a final point I wanted to make about IBM Model 2 is the following. Once we have the parameters q and t, and we'll actually talk next about how to estimate these parameters from training examples. So once we have these parameters, it is very straightforward to find the most likely alignment for a given sentence pair. So what I'm going to describe here is a process which takes in an English sentence paired with a French sentence as the input, and then as output will produce some alignment. So for example, it might produce the following alignment. So for each word in the French sentence, we've chosen one of the English words to align to. And if we have the parameters of IBM Model 2, it's straightforward to find the most likely alignment under the model. Let me show you how this works. So the key definition is the following. So given a sentence pair E1 through EL, F1 through FM, then for each AJ, for j equals 1 to m, you simply find the alignment that maximizes the product of two terms. Firstly, Q of A given JLM, and secondly, T of FJ given EA. So you find the alignment that maximizes this product. Let me illustrate this with a particular example. Okay, so say I want to align this word A in French. So it could potentially be aligned to any one of the English words, or it could be aligned to null. Okay, so any one of these possible alignments is possible, and we have to choose between them. Let's go through each of them in turn and see how this expression is scored. So for the null word, we evaluate Q of 0 given, now we have the third word in the French sentence, and we have 6 as the length of the English and 7 as the length of the French. So that's the distortion parameter, basically specifying the probability that position 3 in French is aligned to position 0. And then we have a translation parameter, t, of A given null. Let's look at the second word, and. In this case, we evaluate Q of 1 given 3, 6, 7, because now we're aligning to the first position in English. And then we have T of A given and. Next word is there. We'd have Q of 2 given 3, 6, 7. And then T of A given this word there in the second position. And so on and so on. We can go right to the end, so the final word is implemented. And that is Q of 6 given 3, 6, 7 times T of A given implemented. So for each of these alternative words that we could align to, we calculate two terms. Firstly, Q, reflecting the likelihood of that position, and then T, reflecting how likely it is that this French word was generated from that English word. And we take the max, so we find the maximum of all these values, and then take the single alignment that maximizes this product. In this case, you'd hope it was this word has, which is the natural translation. Okay, so to recap, the main message here is once we have these parameters, it's very easy to recover alignments. So it's very easy to fill in these alignments on training examples, where an alignment specifies for each French word an alignment to one of the English words, where an English word could include the null position.